Hello and welcome back to the alphabet of astronomy. Today is brought to you by the letter B. So for B, I chose black holes because who doesn't love black holes? They're super cool. This actually relates somewhat to the letter A that we talked about before with AGNs because they're a type of supermassive black holes. So the basic idea of a black hole is an object so dense and massive that nothing can escape from its gravitational pull, not even light. Now you might think, okay, but light doesn't have mass, so why does it even care about gravity at all? Well, we have Einstein to thank for this discovery that gravity actually warps space-time around it, and light follows the curvature of space-time. So as the black hole warps the space-time enough, you eventually get a kind of gravitational well that's so deep that light falls into it and can never climb back out. And if light can't get back out, nothing else stands a chance. So general relativity kind of predicted the existence of black holes, but this was seen as kind of a mathematical oddity, right? Like a quirk of the math and maybe not an actual physical phenomenon. And it was actually Roger Penrose, a 2020 Nobel laureate, who showed in the 1960s that black holes were actually a very robust outcome of general relativity. And since then, we've gone on to learn a lot about black holes. We have a really strong theoretical framework for them, but it is still an active area of research for both theorists and observers, actually. But you might say, how do you observe something that light can't even escape from? An excellent question. I'm glad you asked. So there are a few different ways. So one, even though we can't see light escaping the black hole, we can see the gravitational effects that a black hole has on objects around it. This has really particularly been done for the supermassive black hole at the center of our own galaxy, the Milky Way. And in fact, the other two 2020 Nobel laureates were were responsible for leading this kind of observational effort. But basically, we can watch these stars and clouds of gas that orbit an object, and from that we can learn there is an object of a given mass and size there, and even if we can't directly see it, we know that it's there and we can measure certain properties of it. We can also see matter interacting with a black hole. So as mass falls into a black hole, it releases a lot of energy. And in fact, these are responsible for some of the most luminous and brightest objects in the universe, called AGNs, or active galactic nuclei, which was the subject of the A video of this series, so you can check that out if you want. But these objects are so bright that we can detect them almost throughout the entire universe. In fact, we've detected one that's over 29 billion light years from us. Also, a really, really exciting new thing that we've been able to do just in the past few years is detect the gravitational waves that are emitted by the merger of two black holes. This was first done in 2016, and we've detected several of these events. And so this, again, is a signal that these objects are there, even if we can't see the light from them, because we can see these gravitational waves, which is basically ripples in space-time, which is really awesome that we can detect that. It still blows my mind. And even more recently than the gravitational wave detection, we've actually been able to image the event horizon of a black hole directly, which is crazy because these are really, really small objects, astronomically speaking. And so you need really, really, really high resolution to see them. And so to do this, astronomers basically created a telescope out of several different telescopes located throughout the world, and this is called the Event Horizon Telescope. And this was able to give them a large enough area that they could get a small enough resolution to really look at the event horizon of a nearby supermassive black hole. And they released this image in 2019 of the M87 active galactic nuclei. And you can very clearly see what's called the black hole's shadow in this image. This object is about 50 million light years away, and it's about 6 billion times the mass of the sun. And they had to image it to micro arc-second resolution. So this is actually about 0.01 light years across just the dark shadow, which is less than 1,000 times the distance from the Earth to the sun. So astronomically speaking, a very small object, and remember, this is billions of times the mass of the sun. So very, very dense, like a black hole. So how exactly do you get one of these really kind of crazy objects? Well, gravity is basically pulling things inward all the time. So if you have an object of a given mass, gravity is trying to pull it inward. So you need something to oppose that force of gravity, to kind of hold off gravitational collapse. And so in a regular star, this might be the thermal pressure, right, from fusing elements in its core. So it's producing all of this energy, and as that's radiated out from the core, convected out from the core, various mechanisms, it creates this pressure within the star that kind of holds off the gravitational collapse. Even after the fusion stops because you run out of fuel, there are other more exotic forms of pressure that can resist gravitational collapse. So for a white dwarf, that would be electron degeneracy pressure, and for a neutron star, it would be neutron degeneracy pressure. But if you have something that's dense enough, even these pressures can't stand up to gravity. And so it will collapse basically forever, you can think of it, into an infinitesimally small point that's called a black hole. So it's pretty cool. Gravity is a very persistent force. And the key property that makes something a black hole is really its density, right? You could have something that's billion times the mass of the sun, and if it's big enough, it wouldn't collapse into a black hole. So based on that, we could have a black hole of any size, as long as it was confined to a sufficiently small enough space. However, just because something could exist, theoretically, doesn't mean that we have a way to form it. So how do black holes even form? Well, there's actually several types of black holes, and they might have different formation mechanisms. Again, the general mechanism is gravitational collapse. So all of these is gravity pulling an object in on itself, and there's not enough pressure to resist that, and so it becomes a black hole. But there are different kinds of black holes. So there's what we call stellar mass black holes. So this is kind of the typical black hole where you have a massive star that goes through its life, runs out of fuel, it's too massive to support itself to become a white dwarf or a neutron star, and so it just collapses in on itself and forms a black hole. These kinds of black holes are going to be, no more than 100 times the mass of the sun approximately, maybe up to 1,000 if you're talking about early weird stars. But generally speaking, we're talking 10 to 100 times the mass of the sun. But I mentioned earlier the M87 supermassive black hole, which is billions of times the mass of the sun. So obviously that didn't come from a star that's a billion times the mass of the sun. So how do these supermassive black holes form? Well, that's a great question, and if you know, you should probably tell someone. No, that's a great question, and astronomers don't actually know for sure. But they think that it probably forms over time through the mergers of kind of smaller black holes. They find each other basically, and they merge, and they just build into these larger and larger objects until you have a supermassive black hole. Which would lead one to think that there must be black holes in between this kind of millions of times the mass of the sun and 100 times the mass of the sun. So we call those intermediate mass black holes because it's in between supermassive black holes and stellar mass black holes. But we haven't actually seen any of these yet. There are a few candidates, but they haven't been confirmed. Kind of our best hint as to actually observing these is a recent detection of a gravitational wave from a black hole merger of two black holes that were almost 100 solar masses. And so the resulting black hole was about 140 solar masses. So this is kind of a hint at these intermediate black holes and the process of forming them, but we really haven't seen a lot of them. And lastly, there's a type of black hole called primordial black holes. So basically, the very, very early universe, and when I say early universe, I mean less than a second old, was really, really dense. And so if you had density fluctuations in that very dense environment, those small areas that were more dense than the ones around them could gravitationally collapse into a black hole. And these black holes could be pretty much any size. They could be really, really tiny, or they could be, 10,000 solar masses. So this could give you a very wide range of black holes. However, we haven't actually detected any primordial black holes, and so these are a hypothetical object that we're not totally sure actually exists. Also, if they were too small, they would have radiated away by Hawking radiation since they were born in the primordial universe, but that would be only up to a relatively small mass. So we could still form very, very small mass black holes from primordial black holes that might just be floating around. And astronomers and physicists are really keen to find these and confirm if they exist or not. Primordial black holes have actually been put forth as a possible candidate for dark matter in the universe. So they're very interesting objects that would be really exciting if we could get more confirmation of their existence. So talking about black holes, they are very big, kind of crazy objects. They're very dense. We talked in the AGN video about how they can accrete all of this matter and eject all of this radiation and these jets and stuff. So they seem to be these really violent objects. But they're actually don't have to be. So one thing that I hear a lot is people kind of assuming that something that is a black hole must be, it kind of sucks things in, right? It just like would vacuum everything up. I remember when the Large Hadron Collider first came online, there was some talk about whether this could create black holes, and people were concerned that if it did create a black hole, it would basically eat up the entire Earth. But that's not really the case. So black holes are stable objects, and they don't have to be accreting matter all the time. So if the sun was replaced with a black hole of the same mass as the sun, one solar mass, it wouldn't affect the orbit of the Earth. We would not be sucked into this black hole. We would continue to orbit it relatively normally. I mean, we would die because we wouldn't have sunlight anymore. But black holes can be stable objects. You can have things in stable orbits around black holes as long as they don't get too close. That's called the last stable orbit, before something basically is inexorably drawn into a black hole. So if you get too close to a black hole, yes, you are going to get stretched apart, spaghettified, destroyed, and torn apart into your constituent atoms, which then will release tons and tons of radiation. But if you stay away from a black hole, it's just like any other massive object. And for these very, very small black holes that people were concerned about with CERN, they would not just grow and grow and grow and eat the Earth. They would just dissolve away, kind of, because black holes can dissolve via a process called Hawking radiation. But that's going to be way too much detail if I start getting into that. So hopefully this video was enough to give you a little bit of information about black holes and get you excited about them. But there's obviously way more to learn about black holes. They're a really cool subject that people devote their entire lives to studying. So black holes are awesome. I hope you enjoyed this. I hope you learned something, and I hope you come back again next time. Bye!